Hello and welcome back to Brainwave. Today we're going to be discussing where electrons are within an atom. In the last video we talked about electrons residing in orbitals. The confusing thing about this term is the connotation of orbitals. You immediately think of an electron orbiting the nucleus like a moon orbiting a planet. We described that last time by drawing the nucleus, the centre, as a planet, being orbited by moons, like this and this. While this is a quite nice and simple model to understand, thinking about these electrons whipping around this nucleus in a nice circle, it's simply not correct. An orbital simply describes a 90% probability of where an electron might be. It doesn't say anything about how it is moving, it just tells you where it might be and the energy that it carries. If that's confusing, don't worry, because I think the simplest way of thinking about this is if we use an example. If we take the most common isotope of hydrogen, protium, it has one proton and no neutrons within its nucleus. Let's draw that now. Let's draw the nucleus. There. And because it has one proton and it is an element, it must have one electron. So where could that electron be? We've not got an orbital, but if we think of a sphere that's surrounding this nucleus, we could think of 90% of the time the electron is going to be somewhere within that sphere. It could be here, 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 here. It's going to be somewhere within there. Obviously, because we said 90%, there are going to be points where it's not within that sphere. But for most of the time, it's going to be within that sphere. What we just described there was called a 1s orbital. In the last video, we talked about s, p, d, and f orbitals. Let's start with the simplest, the s orbital. Each of the orbitals can contain a maximum of 2 electrons. So as we said before, if we have hydrogen with 1 electron, and let's draw its nucleus here, it has a single orbital, where its electron is going to be located 90% of the time. We denote this as 1s. Let's add another electron. So let's go for the element helium. Let's draw its nucleus again there. And let's draw this orbital. This is also 1s, because as we've just said, an orbital can contain up to 2 electrons. So let's make a snapshot in time. You can see that hydrogen's electron, let's say it was there, helium's electrons are in there somewhere, so it's containing 2 electrons. But what if we added another electron? Where would that go? Well, as we said, the first 1s level can only hold 2 electrons, so the third electron must be located in a higher energy level orbital. This is called 2s. They're higher energy and are likely to be further from the nucleus and located within this spherical area. So if we look at lithium, let's draw its nucleus here. It has 2s. So let's say that 2 of the electrons are somewhere within there, and 1 of the electrons is going to be in this area around here. Let's look at beryllium. Let's add another electron. So we have 4 electrons in total. This is also 2s. They're higher energy and are more likely to be further from the nucleus and located within this spherical area. What about if we add more electrons? Because boron's got 5 electrons. Where does the 5th go? Well, it goes into the next orbital, which is called a p orbital. There are 3 2p orbitals, and they're perpendicular to each other. They look a little bit like balloons tied together at the end. So let's do another example. If we draw our nucleus again, and draw some axes through it, so we have our y-axis, our x-axis, z-axis, we can then start to describe what these p orbitals look like. When we add our fifth electron, it might be located somewhere within a p orbital, so it could be located somewhere within this. Let's add one more electron. It doesn't go into this one here, the red one, but it would go into another p orbital. Let's add another electron. Again, it won't go into either the red or the green p orbital, but it goes into another p orbital. These p orbitals have further names, so this would be a py orbital, a px orbital, and a pz orbital. If we were to add even more electrons, they would initially start to fill up again. So at the moment we have one electron in this py, we have one electron in the px, and we have one electron in the pz. If we add even more, you'd have 2 electrons in py, then 2 electrons in px, and 2 electrons in pz. So, if we were to say we've got to this point now, and we've filled up all of these p orbitals, just how many electrons do you think we have right now? Pause the video and try and work out how many electrons we have and what element we're talking about. Okay, let's try and work it out. In 1s, we have 2 electrons. In 2s, we also have 2 electrons. And 2p, we have 6 electrons. That gives us a total of 10 electrons, and that gives us the element of neon. If we were to add another electron, where would that go? Well, that would start to fill the 3s orbital, which again is an even higher energy level, and like the levels below, can contain up to 2 electrons. As we add more and more electrons, we fill more and more orbitals. We then need to consider d and f orbitals. So this is my representation of the 5d orbitals. Each one of these orbitals can contain up to 2 electrons. Like the previous orbitals, they can only hold a maximum of 2 electrons. We then move on to the f orbitals, for which there are 7, and you can see the same. And they each hold a maximum of 2 electrons per orbital. While these shapes were initially extremely confusing, we're just building up on what we've previously learned. The principles are exactly the same. These orbitals are just simply representations of where an electron might be.